In this lecture, we provide a quick introduction into the conceptual framework of classical statistics. We use the word classical to make the distinction from the Bayesian framework that we have been using so far. Recall that in the Bayesian framework, unknown quantities are viewed as random variables that have a certain prior distribution. In contrast, in the classical setting, an unknown quantity is viewed as a non-random constant that just happens to be unknown. We can still carry out estimation without assuming a prior for the unknown quantity. For example, if the unknown theta is the mean of a certain distribution, we can generate many samples from that distribution and form the sample mean. The weak law of large numbers then tells us that this estimate will approach, in the limit as n increases, the true value of theta. After going through this argument, we will then take the occasion to introduce some terminology that is often used in connection with classical estimation methods. Now, the sample mean provides us a point estimate for the unknown theta, but does not tell us how accurate that estimate is. To give a sense of the accuracy involved, we introduce the concept of a confidence interval, which is an interval that has high probability of containing the true theta. In general, it is a common practice to report not just estimates, but also confidence intervals. But as we will discuss, one has to be careful in interpreting what exactly a confidence interval tells us. We will see that we can easily calculate confidence intervals using the central limit theorem, and we will discuss in some detail some extra steps that need to be taken if we do not know the variance of the random variables involved. We will then continue in the direction of greater generality. We will see that by repeated use of various sample means, we can also estimate more complicated quantities, such as, for example, the correlation coefficient between two random variables. We will conclude by introducing a general estimation methodology, the so-called maximum likelihood estimation method. This is a method that applies always, even when the unknown parameter of interest cannot be interpreted as an expectation. It is a universally applicable method and fortunately has some very desirable properties. In this segment, we provide a high-level introduction into the conceptual framework of classical statistics. In order to get there, it is better to start from what we already know and then make a comparison. We already know how to make inferences by just using the Bayes rule. In this setting, we have an unknown quantity theta, which we model as a random variable, and so in particular it's going to have a probability distribution. And then we make some observations, and those observations are modeled as random variables, and typically we are given the conditional distribution of the observations given the unknown variable. So these two distributions are the starting points, and then we do some calculations and we use the Bayes rule and we find the posterior distribution of theta given the observations. And this tells us all that there is to know about the unknown quantity theta given the observations that we have made. What is important in this framework is that theta is treated as a random variable, and so it has a distribution of its own, and that's our starting point. These are our prior beliefs about theta before we obtain any observations. However, one can think of situations where theta maybe cannot be modeled as a random variable. Suppose that theta is some universal physical constant, for example, the mass of the electron. Does it make sense to think of that quantity as random, and how do we come up with a probability distribution for that quantity? One can argue that in certain situations, one should not think of unknown quantities as being random, but rather they are just unknown constants. They are absolute constants, it just happens that we do not know their value. Or there may be other situations in which, even though we may think that there is something random that determines theta, we are reluctant to postulate any prior distribution. We do not want to impose any biases. And that leads us to the classical statistical framework, in which unknown quantities are treated as constants, not as random variables. Pictorially, the setting is as follows. There's an unknown quantity that we wish to estimate, and we make some observations x. Those observations are random, and they are drawn according to a probability distribution, and that probability distribution depends, or rather is affected, by that unknown quantity. So, for example, for one value of theta, the distribution of the x's might be this one, and for another value of theta, the distribution of the x's could be a different one. And we're trying to guess what theta is, which in some ways is the question, do my data come from this distribution or do they come from that distribution? In order to make a choice of theta, what we do is we take the data and we process them. And after we process them, we come up with our estimate, or rather estimator. What is the estimator? We take the data and we calculate a function of the data. That's what it means to process the data. And that function is our theta hat. Now, this function, our data processing mechanism, is what we can call an estimator, but quite often, or usually, we also use this same terminology to call theta hat itself an estimator. Now notice that theta hat is a function of the random variable x, so theta hat is actually a random variable, and that's why we denote it with an uppercase theta. On the other hand, after you obtain some concrete data, little x, which are the realized values of the random variable capital X, then we can apply our estimator to that particular input, and we compute a specific value, call it theta hat, lowercase, and that quantity we call an estimate. So this is a useful distinction. Always with random variables, we want to distinguish between the random variable itself, indicated by uppercase letters, and values of the random variable, which are indicated with lowercase letters. Similarly, the estimator is a random variable. It's essentially a description of how we generate estimates, whereas the realized value, once we have some specific observations at hand, that's what we call an estimate. Now let me continue with a few comments. The picture or the setting that I have here suggests that x is just one variable and theta is one variable, but we can have the same framework even if x and theta are multidimensional. For example, x might consist of several random variables, and theta may be a parameter that consists of multiple components. Now you may notice that this notation that we're using here is a little different from our traditional notation, which was of this form. In what ways is it different? The main difference is that here theta is not a random variable. Theta is just a parameter. So what we're dealing with here is just an ordinary, not a conditional distribution. It's an ordinary distribution that happens to involve inside its description some parameters theta. Just to emphasize the point that these are not conditional probabilities because theta is not a random variable, we use a semicolon instead of using a bar. And since theta is not a random variable, we do not include it in the subscript down here when we talk about the classical setting. The best way to think of this situation, mathematically, is that we are essentially dealing with multiple candidate models. As in this picture, this could be one possible model of x. This could be another possible model of x. We have one such model for each possible value of theta.
And if, for example, I were to get data points that sit down here, then a reasonable way to make an inference could be to say these data are extremely unlikely to have been generated according to this model. These data are quite likely to have been generated by this model, so I'm going to pick this particular model. So even though we're not treating theta as a random variable and we do not have the Bayes rule in our hands, we can still see, at least from this trivial example, that there should be a reasonable way of making inferences. And let me close with some comments on the different types of problems that we may encounter in classical statistics. One class of problems are so-called hypothesis testing problems, in which we're asked to choose between two candidate models. So the unknown parameter, as in this example, can take one of two values. So think of a machine that produces coins, and coins are either fair or they have a very specific bias. You want to flip the coin, maybe multiple times, and then decide whether you're dealing with a coin of this type or of that type. There's another type of hypothesis testing problems, which is a little more complicated. For example, this one. We have one hypothesis which says that my coin is fair versus an alternative hypothesis in which my coin is unfair. But notice that this hypothesis actually includes many possible scenarios. There are many possible values of theta under which this hypothesis would be true. We will not deal with problems of this kind in this segment or in this lecture sequence. Instead, we will focus exclusively on estimation problems. In estimation problems, the unknown parameter theta is either continuous or can take one of many values. What we want to do is to design an estimator, a way of processing the data that comes up with estimates that are good. What does it mean that an estimate is good? An estimate would be good if the resulting value of the estimation error, that is the difference between the estimated value and the true value, if that difference is small. You want to keep that difference small in some sense. Well, one may need a criterion of what it means to be small and whether we want this in expectation or with high probability and so on. This statement, to keep the estimation error small, can be interpreted in various ways, and because of that reason there is no single approach to the problem of designing a good estimator. And this is something that happens more generally in classical statistics. Typically, problems do not admit a single best approach. They do not admit unique answers. Reasonable people can come up with different methodologies for approaching the same problem, and there is a little bit of an element of an art involved here. In general, one wants to come up with reasonable methods that will have good properties, and we will see some examples of what this may mean. But again, I'm emphasizing that there is no single best method. So, whereas the Bayes rule is a completely unambiguous way for making inferences, here in the context of classical statistics, there will be some freedom as to what approaches one might take. Let us now discuss a little bit the simplest estimation problem that there is, the problem of estimating the mean of a certain probability distribution, and we will take this occasion to introduce some additional terminology and discuss some desirable properties of estimators. So the context is as follows. We have n random variables that are independent and they're identically distributed. They are drawn from some distribution that has a certain mean, theta, and some variance. We assume that we do not know the value of the mean and we want to estimate it. The most natural way of estimating the mean is to form the sample mean, that is, we take the n observations and take their average. Notice that this quantity, the sample mean, or in this case it is the estimator that we're using, is a random variable because its value is determined by the values of the random variables x1 up to xn. Let us discuss some properties of this estimator. The first property is that the expected value of this estimator is equal to the true mean. This is because the expected value of each one of the x's is theta, and therefore the expected value of this ratio is theta as well. Now, this is a relation that's true for all possible values of theta. Let us appreciate the content of this statement. Let us think what this expectation actually is. More generally, suppose that we are dealing with some estimator which is some function of the data. Then the expected value of this estimator is, using the expected value rule and assuming that we're dealing with a discrete random variable x, the expected value of theta hat is determined as follows. And so we see that the expected value of our estimator depends or is affected by what the true value of theta is. So this is a quantity that generally depends on theta. And what we want in order to have a so-called unbiased estimator is that no matter what theta is, this expectation evaluates to the true unknown value equal to theta. In general, having this property, having an unbiased estimator, is a desirable one. We do not want our estimates to be systematically high or systematically low, no matter what the true value of theta is. A second property of the sample mean estimator is the following. By the weak law of large numbers, we know that the sample mean converges to the true mean in the sense of convergence in probability. Once more, this is a property that's true no matter what the underlying unknown value little theta is. When this is true, this convergence is true for all values of little theta, then we say that our estimator is consistent, or that we have consistency. Having a consistent estimator is definitely a very desirable property. We would like, when we obtain more and more data, that our estimator will give us the correct value. Finally, we would like to say something about the size of the estimation error. This is measured. One way of measuring it, but which is the most common, it's measured in terms of the mean squared error. So theta is the unknown value. This is our estimator, this is the error, we square the error and we take the average. What we've got here for the specific example of the sample mean estimator is the following. Since it is unbiased, we have a random variable minus the mean of that random variable. So this is just the variance of the estimator. And for the sample mean, we know that its variance is sigma squared over n. So this gives us some very specific knowledge about how the mean squared error behaves as we change n. In this particular example, the mean squared error did not depend on theta. It's the same no matter what the true theta is. But in other situations and with other estimators, you might actually obtain here a function of theta. In this segment, we discuss a little more the mean squared error. Consider some estimator. It can be any estimator, not just the sample mean. We can decompose the mean squared error as a sum of two terms. Where does this formula come from? Well, we know that for any random variable z, this formula is valid, and if we let z be equal to the difference between the estimator and the value that we're trying to estimate, then we obtain this formula here. The expected value of our random variable z squared is equal to the variance of that random variable plus the square of its mean. Let us now rewrite these two terms in a more suggestive way. We first notice that theta is a constant. When you add or subtract a constant from a random variable, the variance does not change. So this term is the same as the variance of theta hat. This quantity here, we will call it the bias of the estimator. It tells us whether theta hat is systematically above or below than the unknown parameter theta that we are trying to estimate. And using this terminology, this term here is just equal to the square of the bias. So the mean squared error consists of two components, and these capture different aspects of an estimator's performance. Let us see what they are in a concrete setting. Suppose that we're estimating the unknown mean of some distribution and that our estimator is the sample mean. In this case, the mean squared error is the variance, which we know to be sigma squared over n, plus the bias term. But we know that the sample mean is unbiased. The expected value of the sample mean is equal to the unknown mean, and so the bias contribution is equal to 0. Now, for the sake of a comparison, let us consider a somewhat silly estimator which ignores the data altogether and always gives you an estimate of 0. In this case, the mean squared error is as follows. Since our estimator is just a constant, its variance is going to be equal to 0. On the other hand, since theta hat is 0, this term here is just the constant theta squared, and this gives us the corresponding mean squared error. Let us now compare the two estimators. We will plot the mean squared error as a function of the unknown parameter theta. For the sample mean estimator, the mean squared error is constant, does not depend on theta, and is equal to this value, sigma squared over n. On the other hand, for the zero estimator, the mean squared error is equal to theta squared. How do they compare? Which one is better? At this point, there is no way to say that one is better than the other. For some theta, the sample mean has a smaller mean squared error. But for other theta, the zero estimator has a smaller mean squared error. But we do not know where the true value of theta is. It could be anything, so we cannot say that one is better than the other. Of course, we know that the sample mean is a consistent estimator. As n goes to infinity, it will give you the true value of theta, and this is a very desirable property that the zero estimator does not have. But if n is moderate, the situation is less clear. If we have some good reason to expect that the true value of theta is somewhere in the vicinity of 0, then the zero estimator might be a better one because it will achieve a smaller mean squared error. But in a classical statistical framework, there is no way to express a belief of this kind. In contrast, if we were following a Bayesian approach, you could provide a prior distribution for theta that would be highly concentrated around 0. This would express your beliefs about theta and would provide you with the guidance to choose between the two estimators, or maybe suggest an even better estimator. In any case, going back to this formula, this quantity, the variance of the estimator, plays an important role in the analysis of different estimators. And the more intuitive variant of this quantity is its square root, which is the standard deviation of the estimator and is usually called the standard error of the estimator. We can interpret the standard error as follows. We have the true value of theta. Then, on day 1, we collect some data, we perform the estimation procedure, and we come up with an estimate. On day 2, we do the same thing, but independently. We collect a new set of data, and we come up with another estimate. And so on. We do this many times. We use different data sets to come up with different estimates. And because of the randomness in the data, these estimates may be all over the place. Well, the standard error tells us how spread out all these estimates will be. It is the standard deviation of this collection of estimates. Having a large standard error means that our estimation procedure is quite noisy and that our estimates have some inherent randomness and therefore also have a lack of accuracy. That is, they cannot be trusted too much. That's the case of a large standard error. Conversely, a small standard error would tell us that the estimates would tend to be concentrated close to each other. As such, the standard error is a very useful piece of information to have. Besides designing and implementing an estimator, one usually also tries to find a way to calculate and report the associated standard error. In this segment, we introduce the concept of a confidence interval. The starting point is that an estimate, the value of an estimator, does not tell the whole story. One option is to also provide the standard error of the estimator, but a more common practice is to report a confidence interval. What is that? We will introduce the notion of a confidence interval through a story. You're working for a polling company, you carry out a poll, and then you go and report to your boss that my estimate is this particular number. And then your boss says, I appreciate the 5-digit accuracy, but are your conclusions that accurate? You go back to your desk, you do some more calculations, and then you tell your boss, here is a 95% confidence interval. Your boss tells you, that looks great, but what does that exactly mean? You go back to your textbook, you pull out the definition, and you reply as follows. Well, a 95% confidence interval, so here I'm letting alpha to be 5%. A 95% confidence interval is an interval that has the following property, that the unknown value of the parameter that we're trying to estimate falls inside this interval with probability at least 95%. And if you wish, I could also let alpha be equal to 1%, in which case I could give you a 99% confidence interval. Your boss replies, no, that sounds good, a 95% interval sounds fine. And your boss goes out to the press, holds a press conference, and reports that the true value of the parameter lies inside this range, inside the reported confidence interval, with probability at least 95%. Does this statement make sense? Actually, no. This statement is the most common misconception of what a confidence interval is. To see why this statement does not make sense, look at it carefully. We're talking about the probability of something, but that something does not involve anything random. 0.3 and 0.52 are just numbers, and theta is also a number which we do not know what it is, but it is not random. It is a constant. So this statement is incorrect on a purely syntactic basis. I mean, the true parameter theta either is inside this interval or it is not, but there is nothing random here, and so this statement does not make sense. Instead, let us look carefully at this definition. This statement does make sense because it involves random variables. The lower and the upper end of the confidence interval are quantities that are determined by the data, and therefore they are random. So we do have random variables in here, and so it makes sense to talk about probabilities. To really understand what's going on, think as follows. We're dealing with a poll that is trying to estimate some unknown value theta. You carry out the poll and you come up with a confidence interval based on the data. You might be lucky and your confidence interval happens to capture the true parameter. You carry the poll one more time, maybe on another day, you come up with another confidence interval. And you're again lucky and it captures the true parameter. You carry it on another day and you come up with a confidence interval, and maybe the data that you got were kind of skewed, you were unlucky, and your confidence interval does not capture the true parameter. Having a 95% confidence interval means that 95% of the time, 95% of the polls that you carry out will capture the true parameter. So the word 95% really talks about your method of constructing confidence intervals. It's a method that 95% of the time will capture the true parameter. It is not a statement about the actual numbers that you are reporting on one specific poll. So it is important to keep this in mind and to always interpret confidence intervals the correct way. So how does one come up with confidence intervals? The most common method is based on normal approximations, as we will be seeing next. We now discuss how to come up with confidence intervals when we try to estimate the unknown mean of some random variable or of some distribution using the sample mean as our estimator. So here x1 up to xn are independent, identically distributed random variables that are drawn from a distribution that has a certain mean theta, the quantity that we want to estimate, and some variance sigma squared. Let us say that we want to construct a 95% confidence interval. Our starting point will be the fact that the sample mean, according to the central limit theorem, can be described approximately using normal distributions. And we look up at the normal table and we observe the following, that if we take a standard normal random variable, then there is probability 97.5% of falling below this number 1.96, which means that there is probability 2.5% of falling above that number. And by symmetry, the probability of falling below minus 1.96 is also 2.5%. This means that this middle interval here has probability 95%. And we exploit this fact as follows. If we take the sample mean, subtract the true mean, and then divide by the standard deviation of the sample mean, then we obtain a random variable which is approximately a standard normal. Therefore, what we have here is the probability of an approximately standard normal random variable, or actually its absolute value, falling below 1.96. This is just the event that our standard normal falls inside this middle interval here. According to this entry from the normal tables and the previous discussion, this probability is going to be approximately 95%. And now we take this statement, send this term to the other side of the inequality, and then interpret what it means for an absolute value to be less than something, and we obtain an equivalent statement. This event here is algebraically identical to the event that we have up there, and this provides us with the desired confidence interval. We think of this quantity here as the lower end of the confidence interval. This quantity here is the upper end of the confidence interval, and this statement tells us that there is probability approximately equal to 95% that the confidence interval constructed this way contains the true value of the unknown parameter. So this is how we obtain a 95% confidence interval. If instead we wanted a 90% confidence interval, we would proceed in more or less the same way. Here we would want to have the number 0.95. Why is that? We want this middle interval to have probability 90%, which means that we want to have probability 5% at each one of the tails. And then we look up at the normal tables and we find that the entry that gives us probability 95% of being below that value is 1.645. So if we use 1.645 in place of 1.96, we obtain a 90% confidence interval, and similarly for other choices, for example, if we want a 99% confidence interval. There is only one issue that's left to discuss, and this is the following. In order to obtain numerical values for the endpoints of the confidence interval, we need to know sigma, the standard deviation of the random variables that we are observing. But if we do not know the value of sigma, then we may have to do some additional work. By this time, we know how to construct confidence intervals when we try to estimate an unknown mean of a certain distribution using the sample mean as our estimator. Or actually, these are approximate confidence intervals because we are using the approximation suggested by the central limit theorem. But what if we do not know the value of sigma, the standard deviation of the axis? Then we have a few options. One option is to use an upper bound on sigma. So we will be using a value that's larger than or equal to sigma, and this is going to make our interval somewhat larger. So this is a conservative choice, but it is definitely an option. For example, if we're dealing with Bernoulli random variables, we know that the standard deviation is less than or equal to 1/2, so we can just plug in the value of 1/2 at this point. Another option is to try to estimate sigma. How do we estimate it? We can perhaps use an ad hoc estimate of sigma that fits to the particular situation at hand. So for example, in the Bernoulli case, we know that sigma is given by this formula, where theta is the mean of the Bernoulli. And using this, and since we do have an estimate of theta, this is just the sample mean, we can plug in that particular estimate, and that gives us an estimate of the standard deviation. When n is large, this estimate is going to be very close to the true value, and so this estimate of the standard deviation will also be very close to the true value. Both of these options were discussed for special cases where we have special structure and we can derive an upper bound, or there is a natural estimate that suggests itself. More generally, what can we do? One general option is to use a generic way of estimating the variance, and here's how it goes. The variance is by definition the expected value of something, of this expression. And we can estimate expected values by taking several samples of this quantity and taking the average of them. So if we have n pieces of data, for each piece of data we calculate this quantity, divide by n, and by the weak law of large numbers, this is the sample mean of this particular random variable, and it converges to the expected value of this random variable. So that's how we could estimate the variance. But there is a catch. This expression here involves the mean of the random variable, and this is something that we do not know. So what can we do? Well, we have an estimate for the mean, so we could just plug in that estimate instead of the true value, and this gives us this alternative expression. Now, when n is very large, as n increases, this sample mean converges to the true mean, so this expression here will become closer and closer to this expression. Now, this expression converges to sigma squared, and we conclude from this that this expression will also converge to sigma squared. And so here we have a way of estimating sigma squared from the data, and by taking the square root, we obtain an estimate of sigma as well that we can plug in this expression. And this gives us a complete way of coming up with confidence intervals when we only have data available in our hands, but do not know ahead of time what sigma is. Some remarks. This procedure of constructing confidence intervals involves two separate approximations. One approximation has to do with the fact that the sample mean is approximately normal according to the central limit theorem. And then there is a second approximation that comes in using an estimate of sigma instead of the true value of sigma. Now, when we estimate sigma instead of using the true value, we're introducing some additional randomness in this procedure, and because of this randomness, the confidence intervals actually should be a little larger. There is a systematic way of doing that, and it involves using the so-called t-distribution tables, and those tables are going to give us certain numbers that are a little different from what we have here. So instead of 1.96, we might have a somewhat larger number. This correction is relevant when n is a small number, let's say n smaller than 30. But for larger values of n, this correction, where we use t-tables instead of normal tables, is rather insignificant and one doesn't bother with it. In any case, we will not discuss any further this additional correction, but it is useful to know that it is something that statisticians will often do. Finally, one last remark. One will often see an alternative way of estimating the variance, where instead of this factor of 1 over n, one uses a factor of 1 over n minus 1. With this alternative form, it turns out that this is an unbiased estimator of the variance, and that could be a reason for preferring to use this alternative form. On the other hand, when n is large, whether we use n or n minus 1 makes very little difference. And this concludes our discussion of confidence intervals. As we have already discussed, we can estimate an unknown mean of a certain random variable by generating several independent samples of that random variable and taking their average. And this procedure is well justified because of the weak law of large numbers, which tells us that this estimator converges when n goes to infinity, in probability, to the true mean. Now we can apply this idea more generally. Suppose we want to estimate the expected value of a function of a random variable x. Now g of x is itself a random variable, so if we have samples of g of x, we can use the same procedure. How do we do that? We generate independent samples of x, and these give us independent samples of g of x. We use those independent samples, we average them, and by the weak law of large numbers, this quantity, as n goes to infinity, will converge in probability to the expected value of g of x. We already used an idea of this form when we tried to estimate an unknown variance. A variance is defined as an expectation, and now we can generate samples of x, many independent samples, calculate this quantity and take the average. However, we might not know the mean of the distribution, so instead of the true mean, we use an estimated mean, which is estimated the usual way using a sample average. So when n is large, this estimated mean is close to the true mean, so using the estimated mean here will not make a substantial difference. And then we have essentially independent samples of this quantity, and by averaging them, we obtain an estimate of the variance, which asymptotically, as n goes to infinity, will be equal to the true variance. Now we can push this idea even further. Suppose we wish to estimate a covariance. What's a natural way of doing this? We can generate independent samples of the pair of the random variables x and y, so this will be a typical independent sample, and replace the expected value by a sample average. That is, we take our ith sample, our ith pair, and calculate this quantity, which looks very much like the quantity in here, except that we're using the estimated means in place of the true means. We obtain these quantities and average n of them. Again, using the weak law of large numbers, one can argue that this estimate will converge to the true value of the covariance as n goes to infinity. And once we have estimates of a covariance and of variance, then we can use that to estimate correlation coefficients. Look at this formula, which is the definition of the correlation coefficient. If we just replace all quantities involved here by corresponding estimates, this gives us an estimate of the correlation coefficient. All of these ways of forming estimates can be shown. We are omitting the details of the argument, but hopefully you get the idea by now. All of these quantities are consistent estimators. That is, when the sample size goes to infinity, they approach the correct values of what we're trying to estimate. So this is just an opening of what else a statistician might be interested in. And if you're wondering what's the further agenda after this point, it would be something like the following. Typically, a statistician might want to say as much as possible about the probability distribution of an estimator. For example, we have here an estimate of the covariance. This estimate is going to be a random variable because it is determined by random quantities. What is the probability distribution of this quantity? Can we describe it approximately? What is the mean squared error associated with this estimator? And if you wish to construct confidence intervals, how would you do it? These are all topics that statisticians have studied in depth, and you could see more about these topics if you were to take a further class on statistics and inference. But we will not go any deeper in this course. We will finish our discussion of classical statistical methods by discussing a general method for estimation, the so-called maximum likelihood method. If an unknown parameter can be expressed as an expectation, we have seen that there is a natural way of estimating it. But what if this is not the case? Suppose there is no apparent way of interpreting theta as an expectation, so we need to do something else. So rather than using this approach, we will use a different approach, which is the following. We will find a value of theta that makes the data that we have seen most likely. That is, we will find a value of theta under which the probability of obtaining the particular x that we have seen, that probability is as large as possible. And that value of theta is going to be our estimate, the maximum likelihood estimate. Here I wrote a PMF. That's what you would do if x was a discrete random variable, but the same procedure, of course, applies when x is a continuous random variable. And more generally, this procedure also applies when x is a vector of observations and when theta is a vector of parameters. But what does this method really do? It is instructive to compare maximum likelihood estimation to a Bayesian approach. In a Bayesian setting, what we do is we find the posterior distribution of the unknown parameter, which is now treated as a random variable, and then we look for the most likely value of theta. We look at this distribution and try to find its peak. So we want to maximize this quantity over theta. The denominator does not involve any thetas, so we ignore it. And suppose now that we use a prior for theta, which is flat. Suppose that this prior is constant over the range of possible values of theta. In that case, what we need to do is to just take this expression and maximize it over all thetas. And this looks very similar to what is happening here, where we take this expression and maximize it over all thetas. So operationally, maximum likelihood estimation is the same as Bayesian estimation, in which we find the peak of the posterior, for the special case where we're using a constant or flat prior. But despite this similarity, the two methods are philosophically very different. In the Bayesian setting, you're asking the question, what is the most likely value of theta? Whereas in the maximum likelihood setting, you're asking, what is the value of theta that makes my data most likely, or what is the value of theta under which my data are the least surprising. So the interpretation of the two methods is quite different, even though the mechanics can be fairly similar. The maximum likelihood method has some remarkable properties that we would like now to discuss. But first, one comment. We need to take the probability of the observed data given theta, this is a function of theta, and maximize it over theta. In some problems, we can find closed form solutions for the optimal value of theta, which is going to be our estimate, but more often, and especially for large problems, one has to do this maximization in a numerical way. This is possible these days, and routinely people solve very high dimensional problems with lots of data and lots of parameters using the maximum likelihood methodology. The maximum likelihood methodology is very popular because it has a very sound theoretical basis. I will list a few facts which we will not attempt to prove or even justify, but they are useful to know as general background. Suppose that we have n pieces of data that are drawn from a model from a certain structure. Then, under mild assumptions, the maximum likelihood estimator has the property that it is consistent. That is, as we draw more and more data, our estimate is going to converge to the true value of the parameter. In addition, we know quite a bit more. Asymptotically, the maximum likelihood estimator behaves like a normal random variable. That is, after we normalize, subtract the target and divide by its standard deviation, it approaches a standard normal distribution. So in this sense, it behaves the same way that the sample mean behaves. Notice that this expression here involves the standard error of the maximum likelihood estimator. This is an important quantity, and for this reason people have developed either analytical or simulation methods for calculating or approximating this standard error. Once you have an estimate or an approximation of this standard error in your hands, you can further use it to construct confidence intervals. Using the asymptotic normality, then we can construct a confidence interval in exactly the same way as we did for the case of the sample mean estimator, and this, for example, would be a 95% confidence interval. Finally, one last important property is that the maximum likelihood estimator is what is called an asymptotically efficient estimator. That is, it is the best possible estimator in the sense that it achieves the smallest possible variance. So all these are very strong properties, and this is the reason why maximum likelihood estimation is the most common approach for problems that do not have any particular special structure that you can exploit otherwise. In this segment, we will go through two examples of maximum likelihood estimation, just in order to get a feel for the procedure involved and the calculations that one has to go through. Our first example will be very simple. We have a binomial random variable with parameters n and theta. So think of having a coin that you flip n times, and theta is the probability of heads at each one of the tosses. So we flip it n times and we observe a certain numerical value, little k, for the random variable k. And on the basis of that numerical value, we would like to estimate theta. According to the maximum likelihood methodology, the first step is to write down the likelihood function. This is the probability of obtaining this particular piece of data if the true parameter is theta. Now, since k is a binomial random variable, the probability of obtaining k heads in n tosses is given by this expression here. So what we need to do is to take the data that we have observed, plug it in this formula, leave theta free. We have here a function of theta, and then maximize this function of theta over all theta. Let us now do this calculation. Actually, instead of maximizing this expression, it's a little easier to maximize the logarithm of this expression. And the logarithm of this expression is as follows. There's a first term, which is the logarithm of the n choose k term. Then the logarithm of theta to the k is k times log theta. And finally, the logarithm of the last term is n minus k log of 1 minus theta. So we need to maximize this expression with respect to theta. In order to do that, we take the derivative with respect to theta. Here there is no theta involved, we get a contribution of 0. This term has a derivative of k divided by theta, and this term here has a derivative which is n minus k times the derivative of this logarithmic term, which is 1 over what is inside the logarithm, but by the chain rule, because of this minus sign here, we get also a minus sign and we obtain this expression. Now at the maximum, the derivative has to be equal to 0. And this gives us now an equation for theta that we can solve. Let us take this term, move it to the right-hand side, and then cross-multiply with the denominators to obtain the relation that k minus k theta, this is obtained by multiplying this k with this 1 minus theta factor, has to be equal to this term times theta, which is n times theta minus k theta. The k theta terms cancel, and we're left with this expression, which tells us that theta should be equal to k over n. So this is the maximum likelihood estimate for this particular problem, which is a pretty reasonable answer. If you would like to rephrase what we just found in terms of estimators and random variables, the maximum likelihood estimator is as follows. We take the random variable that we observe, our observations, and divide it by n, and this is now a random variable which will be our estimator. Now notice that in this particular example, the answer that we got is exactly the same as the answer that we got in the context of Bayesian inference when we were finding the maximum a posteriori probability estimator, but for the special case where the prior was a uniform distribution. So if we assume that theta is actually a random variable but has a uniform distribution, so that we have a flat prior and we carry out maximum a posteriori probability estimation, we do obtain exactly the same estimate. And this is consistent with the comments that we made earlier, that maximum likelihood estimation can be interpreted also as map estimation with a flat prior. Let us now move to our second example, which will be a little more complicated. Here we have n random variables that are independent, identically distributed. They all have a normal distribution with a certain mean and variance. But both the mean and the variance are unknown, and we want to estimate them on the basis of these observations. The first step is to write down the likelihood function. That is the probability density function for the vector of observations given some set of parameters. Because of independence, the joint distribution of the vector of x's that we have obtained is the product of the PDFs of the individual x's, of the xi's. So the PDF of a typical xi that has variance v and mean mu is of this form. So this is the likelihood function in this case. This is the probability density of obtaining a particular vector x of observations when we have these particular parameters. We would like to maximize this function. As in our previous example, it is actually a little easier to maximize the logarithm of this expression. And this is the same as minimizing the negative of the logarithm of this expression. Now, when we take the logarithm of this expression, we have a product, so we're going to get a sum of logarithms, and I leave it to you to verify that the negative logarithm of this expression is of this form, plus some other constant that does not involve the parameters, and which comes from this factor of 1 over square root 2 pi. In particular, this term here appears when we take the logarithm of this, and this happens n times because we have the product of n terms, And this term here appears when we take the logarithm of this expression and after we put in the minus sign because we're actually considering the negative of the logarithm. Now to carry out the minimization, what we need to do is to take the derivative of this expression with respect to mu, set it to 0, and also take the derivative with respect to v and set it to 0 as well. Solve those equations and find the optimal mu and v. So let's start by optimizing with respect to mu. So we're going to take the derivative of this expression with respect to mu and set it to 0. This term does not involve mu, so we only need to take the derivative of this, and the derivative of this is going to be, there's a term 1 over v, and then the derivative of a quadratic divided by 2 is just xi minus mu, and we have one term for each possible I. We get this equation. Now we can cancel out v, and we're left with the equation that the sum of the xi's is equal to the sum of the mu's, which is n times mu. And now we can send n to the denominator to obtain that the estimate of mu is going to be the sum of the xi's divided by n. So the maximum likelihood estimate of the mean takes a very simple and very natural form. It is just the sample mean. Now let us continue with the minimization with respect to v. In order to carry out that minimization, we need to take the derivative of this expression with respect to v and set it to 0. The derivative of the first term is equal to n over 2 times 1 over v. And then from here, when we take the derivative, we obtain the sum of all these terms divided by 2v squared. But actually, when we take the derivative of 1 over v, the derivative is minus 1 over v squared. And for this reason, here we will have a minus sign. So this is the derivative with respect to v. We set it equal to 0 and carry out some algebra. What is the algebra involved here? We can delete this term 2 that appears here and there. This term v cancels out this exponent here. Then we take this v, move it to the other side, and then take this n and move it to this side underneath this term. And finally, what we obtain after you carry out this algebra is this expression, that the estimate of the variance is some form of the sample variance where we use the value of the optimal value of mu, and the optimal value of mu we have already found. It's given by this expression here. So we obtain a pretty natural estimate for the variance as well by using this maximum likelihood methodology. Now, these two examples were particularly nice because the algebra was not too complicated and the answers turned out to be what you might have guessed without using any fancy methods. But in other problems, the calculations may be more complicated and the answers may not be so obvious.